So last week we focused on some approaches for telling stories in the general sense, and all of you chose to focus on non-data stories. So hopefully the experience of putting together your own stories and like seeing how it was received by the class and seeing your classmates' approaches helped give you some useful practice with the storytelling process. And we're going to keep building on that process as we continue in the course. And then, you'll be telling many more stories as we go. But for the rest of the course, we're going to be shifting gears somewhat to focus specifically on stories about data. So in other words, like stories whose major characters and plot points and illustrations, themes, and messaging are all driven by data and all backed up by data. And just like there's no right way to tell a narrative story, there's no one right way to tell a story about data. But just like we saw for this first assignment, different approaches and strategies may be differently effective at conveying different data stories or particular data stories. So we'll use many of the same ideas that you learned about in Module 1 when we're putting our data stories together. But we're thinking about the kind of difference in the material that you're going to be communicating. So for this week, your main job is going to be putting together your first data story as part of assignment 2, and that's going to be due on Thursday at midnight. This week is going to work similarly to last week, where we're going to have some discussion and lecture for the rest of today. And then on Wednesday, we'll workshop your stories. And then on Friday, we'll critique each other's stories and get some feedback. And also, just like for this assignment, there's no coding required for assignment 2. If you happen to have taken a look at the assignment 2 instructions, you'll notice a lot of similarities between assignment 1 and 2. So the data story you put together this week has to use data, but it can, just like story 1, be about anything, including something fictional. So you can make up data to better tell your story if that's what you want to do. You can make up data for some fictitious place or event, etc. And then you can also base your story off of one or more existing stories if you want. But if you choose to do that, then you'll need to retell the story in a new way or with a new interpretation to kind of make it yours. And then the key things to focus on for this next assignment are how you can use data and data visualizations as effective narrative aids, kind of analogous to the images used in your first story. And then also, how can you make your story interesting and meaningful while also being constrained to focus on data, which can sometimes be kind of boring or dry. So that's tricky. So before Wednesday, you should take a look at the assignment instructions if you haven't done so already. And then come to class on Wednesday with some ideas for us to build on and workshop. Any questions about assignment 2 before we continue?
Could you clarify what you mean by if you're retelling an existing story, putting a spin on it? Just because if it's a data story, does that I feel like a lot of stories would be already told if we're not coding our own data. Does that make sense?
Well, the idea is if there's some narrative that I guess it might help if you're thinking of a concrete example, but that's something we could workshop. But the idea is if there's some kind of famous or known story out there, I guess it could be famous to you, even if it's not famous to others. Can you you could take an existing story and tell it in a different way or interpret the data in a different way. So there's to some extent there's the data is kind of fixed, but then your interpretation is what can change, and the way which things you emphasize, how you interpret it, what other information you bring in that's kind of where your degrees of freedom could be if you want to tell an existing story.
Okay. Yeah. Thank you.
Sure. Okay. Um, any other questions?
So, what should the visuals look like in a story like this?
So yeah, so we'll talk about some data visualization stuff today. But yeah, that's a great, but they're going to be like, you could use photographs and video clips just like you did for your first story, or I mean, or even drawings if you want. But then you also are going to want to tie in like, I mean, you can sketch them out. So there's, like I said, there's no coding. So you can draw a figure, but you want to use like data visualization techniques. So we'll talk about that, for the rest of class today. To give you some kind of things to think about. That's a great question. So, so I mentioned last week that I see the storytelling part and the data part of storytelling with data as like partially separable. And so now that we've gotten some practice with the storytelling part without being burdened by thinking about the data, it's a good time for us to start adding in like some data stuff. So mostly for this course, that's going to be about visualizing data in ways that help you tell a story. And so that's why this week we're going to be getting acquainted with data visualization. And then as a quick aside, another important aspect of the data part of storytelling with data is carrying out statistical analyses and checks to back up your claims. And we're going to largely ignore the statistics aspect of data storytelling in this course. But if you've taken a stats class already, then you'll have gotten an introduction to some of the key ideas. But for this term, we're essentially going to be using visualization as the key way of finding underlying patterns. So we're not going to explicitly have to remember anything you learned about in your stats courses. But that being said, if you decide you do want to use statistical approaches as we progress in the course, I'm happy to help brainstorm how to set up your tests and provide feedback and that sort of thing, but it's not strictly required. But that is a difference from real world data science where so to speak, in kind of real data science, like if you're working for a company or a research organization, you would often need to do additional statistical analyses to like back up what you're saying. So if you go into a data science role after my course, or do this professionally, then you'll need to synthesize what you learn this term and what you learn in your stats courses to really do that stuff. Okay. So next, I want to take some time to get us all in the right mindset for thinking about data visualization. So the first thing I want you to think about is, think back to the visualizations that you and your classmates put together for your first assignment. So can you think of any visuals that really stood out for you as particularly effective? Maybe we could just mention a few of them. What stands out in your minds?
I'm thinking about Hannah's news clippings that she had in her story. I thought those were effective.
So splicing in the little news clips. Yeah, I agree.
As we mentioned, I thought Nathan's use of the calendar really brought us into the moment.
Cool. Yeah. So to dig into that a tiny bit more, representing a calendar is a great way of representing dates. It's a useful tool that we all rely on and are familiar with. So communicating, it's kind of like the right tool for the job for communicating date sorts of information. So yeah, I agree that was really effective. Similarly with your Google Maps, Nathan, that was, ideal for communicating spatial information. Okay, cool. Well, think about that. Part of what makes a good story visual in the general sense also applies to the specific case of data stories. So for example, like, you want to create figures that complement the narrative or convey a clear message in a compelling and memorable way, and like try to make them visually pleasing and that sort of thing. But like, can you think of some important differences between like data-based illustrations and the sorts of illustrations you used in your stories last week, or like that you might see in like a picture book or a Pixar movie or something like that?
I think like interpretation is a big one. I think it's like pretty easy to see a calendar and know what a calendar is, or to see like an image and know what that is. But it's different to see some graphs are like super duper complicated, and it's like, okay, what is this actually showing? What does this really mean? So there's more of a maybe a disconnect if it's not like super intuitive.
Yeah, sort of going off that, in the module 2, it's talking about how you're supposed to like minimize the non-data ink. So like just keep it like as simple as you can and not have all these like extra things on it. But I feel like if you're doing a drawing for like a non-data story or like a Pixar movie, for example, like sometimes it can be really exciting and like entertaining to have all kinds of stuff that people can like jump around and look at, which is like the opposite of what you want with like a graph.
I think of like oh sorry, Nathan, you're about to talk.
Oh, no, you got it.
I think of like animations at least, or like drawings or visuals in our last week's assignment as a way to like add to the story in a way. So like you're narrating the story and it adds to it. But when it comes to like a data visualization, I would feel compelled to like explain the graph and have my story divert from a narrative to like actually have to explain the graphic instead of the graphic on its own helping the story. So that's something interesting I think I'm gonna have to explore this week.
That's a really interesting point. It's a tricky balance. You want your graphics to be like sufficiently intuitive that you don't have to divert too much, but you're right. But that's a good observation that sometimes you do have to kind of unpack it. Yeah. Okay. Yeah. So, sorry, Nathan, did you have something also?
I was just gonna say like choose like the right like graph, like maybe like a pie chart's better for a situation, or like a bar chart would be better.
Yeah. Always a good thing to do. Yeah,
Kind of
totally.
like, I think people know that though, but yeah.
Yeah. Okay. Yeah. So we're thinking about this stuff. So I wanted to kind of give you a kind of whirlwind tour of different data visualization like approaches and strategies, and kind of a way of framing. So let me share my screen so that, let's see. Okay. Can you all see the slideshow there? Okay. Okay. So, and can you see my mouse pointer? Okay. So, actually, sorry, one sec. Just realizing I'm gonna. Okay. Let's see if this works. Okay. So I want to expand on the material that is in module 2 a little bit, and also, emphasize some of the key concepts that I want you to take away. So there's a lot to take in. So these slides are my attempt at helping to make the material a little bit more digestible. And let me also paste in a link to the slides into here, in case that's useful. And then let's see, there's a lot to go through in these slides. I'm going to try to kind of power through and get through the full thing. But feel free to jump in with questions or comments. And given the time it is now, I may go over time. So I'll just say now, if you need to sign off, just go for it. And, you can catch the last parts in the recording if needed. I'll do my best to power through, but depending on how much discussion there is, might not get through the whole thing. Okay. So from one perspective, data sets are often pretty simple. They're kind of just like collections of values like numbers and text and images and sounds and that sort of thing. So in a sense, simply printing out a table of those raw values is the most accurate way that we could predict or depict the data. But that's also likely an ineffective visual aid. So for example, the complexity of many data sets comes from the fact that they're very large and our brains are just not good at quickly processing vast tables of numbers. So here's an example of that. On the right, I'm showing pixel intensity values of a grayscale image. And at least to me, it's pretty difficult to interpret those numbers. Wheels of delight in the background there. From as any sort of meaningful pattern. But when you display the table as a visual image, like on the left, then you can see that it's a low resolution image of a face. You might even be able to recognize that it's Abraham Lincoln. So the fundamental job of our visual systems is to take in measurements of millions of tiny neurons in our retinas and interpret those numbers as meaningful patterns. And in everyday life, we rely on our visual system and our other sensory systems to guide our behaviors and make decisions and process and remember what's going on around us. But we can hack into the visual system's ability to quickly interpret vast amounts of information to also communicate information about data. And conveying the patterns that we want people to perceive means figuring out how to turn data into pictures. Another important reason for depicting data visually is that statistical summaries are often misleadingly impoverished. So a classic example is called Anscombe's quartet. And this is invented or discovered by Francis Anscombe, who was an English mathematician. And Anscombe's quartet is made up of the 4 data sets shown here in these scatter plots. So each point in each panel shows like the XY values of a single data point from a single data set. And the surprising thing about these 4 data sets is that they appear very different when you plot them visually, but many of their statistical properties are identical. So for example, all 4 data sets have the same mean X and Y values and the same variances for X and Y, the same correlations between X and Y, the same best fitting regression lines, etc. So if you were to summarize these data sets using the sorts of statistical tools that you might have learned about in your introductory to stats courses, they'd all look the same from that perspective. A more recent version of Anscombe's quartet is called the Datasaurus Dozen. It's kind of a fun one. This one was created by Alberto Cairo. You can see that the mean and standard deviations of the X and Y values of all of these data sets and the correlations between X and Y within each data set are all preserved, even though the data sets look very different when we plot them on scatter plots. And then another neat feature of this animation is that those properties hold even, those statistical values are preserved even during the warpings from each data set to the next. That's kind of fun. Okay, so if you're at least partially convinced by these examples that visualizing data can be useful, we still need to consider like how we're going to turn raw data into specific figures. So one way of helping to define and think through the options is called the grammar of graphics. And essentially, the grammar of graphics is a language for describing all possible figures that we could make. And the fundamental idea is to separate the pipeline that starts with the data and ends with a figure into a specific sequence of separable steps. So according to the grammar of graphics, each step in the data visualization pipe is called a layer. And each layer affects how the final figure looks, but it can work independently of the other layers. So the data layer defines the raw data set that we'll be visualizing. And then the aesthetics layer defines which aspects of the raw data will be considered in subsequent steps of the visualization pipeline. So for example, if our data set is a series of measurements taken from a fish swimming around a fish tank, then the raw data might be a table where like each row is a set of 10 measurements taken at a particular point in time. And then those measurements would each go in a different column. So maybe they like specify the fish's X, Y, and Z position in the tank at a given point in time. And then maybe it's like yaw, pitch, and roll. And then like the other properties might reflect the fish's appearance or like what it was doing at each moment. So if we were only concerned with the fish's movement through the tank, then we could define an aesthetic of the data set that discarded everything except the X, Y, and Z positions. Or we could also do something fancier, like where we look at combinations of columns in the original data set. So you could have like the color be dependent on the yaw, pitch, and roll or something like that. And then anything that's not specified in the figure's aesthetic is going to get ignored in subsequent steps of the pipeline. The geometries layer defines a set of primitive shapes that we'll be using to represent the data. So for example, in a bar graph, the primitives might be like rectangles, or in a line plot, the primitives might be lines, or like in a scatter plot, the primitives might be circles or squares, and so on. So the primitives can also be complicated. So if we were creating a map, then a primitive shape might be defined by the border of a state or a country. The facets layer defines different subplots of the figure. So subplot is like a panel in the figure. And each facet of the data set goes in a different subplot. So for example, the Anscombe's quartet figure shows each of the 4 data sets in a different subplot. So for that figure, if the raw data comprised a set of XY coordinates, along with labels saying which of the 4 data sets each observation belonged to, then we could specify that the group labels or the data set labels should be used to specify like the different facets or subplots in the final image. Next, the statistics layer is used to specify statistical models or summaries. So for example, if we wanted to add a regression line to our figure, that would be specified in the statistics layer. And for some types of plots, like histograms or probability distributions, the statistics layer might compute like the mean or the median of different data dimensions that are specified in the aesthetic layer. The statistics layer might count up the number of times each unique value appears or that sort of thing. But it can also be really simple. So like the identity function could be used as a statistic, and that would just take the data aesthetics that we've specified and return the same values without changing them or computing anything. So you could use that to make a scatter plot as an example. Next, the coordinates layer specifies how to actually plot the coordinates in the data representation space that were specified in the aesthetics layer and potentially transformed by the statistics layer. So in other words, the coordinates layer says, if I'm trying to show this particular shape, how do I actually like display it on the screen? So we might want to show the data on a like Cartesian plane or in polar coordinates or on a geographic map or any other map or coordinate system that we want to define, a brane, etc. And then finally, the theme layer specifies non-data elements of the figure like axis labels and color schemes and titles and things like that. Okay, a lot of stuff there. So the 2 grammar of graphics papers that I linked to in the module 2 material take you through the process of like actually specifying different types of plots that you might be familiar with using the grammar of graphics framework. And I'd recommend you take a look at those papers if you haven't already, but it's not critical that you memorize these ideas. What I want to take you to take away from the grammar of graphics framework is that it provides one approach to thinking really, really systematically about the set of figures we might want to create in order to visualize our data. And the framework is flexible enough to encompass any visual figure that humans have ever made or will ever make. So the like expressive power is really enormous. But by giving us some structure regarding how we think about figures, the grammar of graphics can help us make like intentional design decisions and understand what the effects of those decisions are. So later on in this course, you might choose to work with a plotting toolbox that allows you to directly specify figures using the grammar of graphics. So if you decide to go in that route, then you'll want to spend some time really like understanding the different layers and like replaying the recording of that last slide until it sticks in your brain. Or you might want to decide just to like gain a more superficial understanding and just like use these ideas to indirectly organize or influence your thoughts. And either one is fine. Okay. So to help guide your design process, you can start by considering whether you'll want to display the raw values of your data set or a summary or both. And that might be determined in part by how big and complicated your data set is, and also like how readily the aspects of the data that you care about can be encompassed by summaries. You should also consider or think about whether your data are discrete or continuous. Discrete data are things that take on integer values like counts, or things that can't have infinitely high precision, like digital measurements. And then continuous values are usually analog, and they can take on any real number or like any real number within some range. Another way of thinking about the discrete versus continuous distinction is about how the samples are taken or measured. So for example, if you have a set of unordered observations from each of several categories or individuals, then there might not be a natural progression across those observations. So in that case, your observations would probably be discrete. But if you have ordered observations, like measurements taken at different time points or at like systematically varying locations, then you might think of them as continuous. If your data are discrete, you might want to show that in a plot of the raw data by keeping the individual data points or categories visually separated, or you could denote continuous data by connecting the data points. And then the third consideration to keep in mind is what pattern you ultimately want to explore or emphasize in your figure. So you want to pick a data visualization approach that has the potential to reveal those patterns. Otherwise, you'll never find them or convey them. And then the overarching goal that guides your figure design process should be the message that you're trying to communicate. So you want to make your point as clearly and intuitively as you possibly can. Okay. So for the rest of class today, I'd like to kind of bombard you with a bunch of examples of different types of figures. And I've organized them into broad categories, like whether the plots display raw data or summaries, or like what coordinate systems they use. And then I've also chosen some examples of figures that highlight particular types of patterns that you might find useful or interesting. So as I'm flipping through, I'll like say a little bit about each figure, and you should think about which figures look interesting to you, and like how you might be able to use them, or what messages you might be able to communicate with the different types of figures. And then another important thing to think about is the kind of wow factor of different figures. So some figures just look more visually interesting. So pay attention to what figures stand out to you or speak to you. And you might want to make use of those in your projects or stories. You don't need to memorize these figures. You'll have access to the slideshow in the link I just posted, and also you get the recording of today's meeting. And I should also note, this is not a complete survey of all possible plot types, but I'm hoping it's going to get you thinking about different ways of visualizing data. Okay. Cool. Okay, so the first group of plot types I want to show you is about displaying the raw data. So you're going to have seen some of these types of figures in the Module 2 material. Okay, so a table is just a printout of the raw data set. It's kind of the most raw form of the data. A bar graph shows one number about each observation as a different bar, and then the heights of the bars reflect the values of those observations. And then bar heights can be positive or negative, and the bar colors can be set to convey additional information, or to help convey or make visual comparisons easier. And bar graphs can be displayed like this, vertically, or with the bars going horizontally. Either is equally fine and correct. To facilitate comparisons between groups, you can use grouped bar plots. Each color here reflects a different group, and then the groups are separated along the x-axis according to some other dimension of the data. These are types of penguins. Okay. Stacked bar graphs are useful when you want to illustrate both the total values across groups and also the individual group contributions. Scatter plots map specific data dimensions or properties onto the XY plane. And then you can use color and shape to denote different categories or conditions in your data set too. You can also create 3D scatter plots to highlight additional data dimensions or features. It can sometimes be hard to read 3D scatter plots if there's too much going on, but they can also be really useful sometimes, particularly if you have like interactive or animated plots where you can like examine the figure from different views. In heat maps, you're converting each entry in a table into a color value. A heat map can be used to display an image like a photograph, or also any other type of like tabular or tabulatable data. A volume plot is like a 3D analog of a heat map. Each cube in the plot gets colored according to the value in a 3D table or a tensor. These are used a lot in neuroscience applications. So for example, like to visualize the brain. So here I'm showing a volumetric brain plot on the left and then slices of the plot on the right. Okay. The next type of plots I want to go over are aimed at creating summaries of the data rather than depicting individual data points. So one way of summarizing the data is to compute a bunch of statistical properties of your data set and then display them in a table. So it's not particularly visually pleasing or intuitive, but sometimes this format can be useful. So I use these sorts of reports myself as like mainly as debugging tools when I'm trying to quickly compare different data sets or groups within a data set. But then they need to be supplemented with other visualization approaches, like we saw in the Anscombe's quartet and DataSource dozen examples. So they don't tell you everything. Histograms display the number or sometimes the proportion of data points whose values fall within a particular range. So it shows how the values are distributed in the data set. Visually, histograms look kind of similar to bar plots, but the difference is that the x-axis positions in histograms carry information, and each bar reflects data from a potentially different number of observations whose groups are determined by their values rather than some other label. And then a density plot is highly similar to a histogram. So that looks like the darker blue curve in this figure. And it's like a histogram, but it uses a smoothing process to create a continuous smooth curve that approximates what proportion of the data took on each possible value along the x-axis. Histograms and density plots can also be shown in 2 dimensions like this. 2D histograms and density plots highlight how different dimensions of the data are related to each other. So for example, if you see like an oriented ellipse in the 2D histogram, it means that the 2 dimensions that you're showing are related to each other or correlated. And then in this example, you can also see 1D density plots on the top and right of the figure. And that can be useful for showing how the values along one dimension at a time are distributed. Ridge plots look really neat. They're kind of like a bunch of mountains receding into the background. Each row shows the density plot for some condition or data set. And then often the rows are ordered along some measurement dimension. So for example, you might use a ridge plot to show the distribution of some measurement varying over time, where each row is a different time point or range of time points. And then in this example, color is also used to distinguish the rows, and that can be a useful way of highlighting differences or providing a convenient way of referring to the rows. And then this example also labels each row with its own letter, although that's somewhat non-standard. This figure shows a scatter plot, which displays the raw data. But then the additional line that's been added here shows the underlying trend in the data, or like how the X and Y coordinates are related. And then visually, regression lines can help emphasize trends in the data. A vector field, which is also sometimes called a quiver plot, shows directional data. Got a loud 4-year-old here. Okay. At each point on a grid, the vector field plots the direction of movement for all data located at that point or in that kind of grid square. And then in this example, the angles are indicated by the arrow directions and also by their colors and lengths. So vector fields are great for summarizing any sort of movement pattern, like currents or traffic flow patterns or migration patterns, that sort of thing. A streamline plot is similar to a vector field or quiver plot. So if you imagine like first drawing a vector field, each line in a stream plot is drawn as a tangent to the angles in the vector field. And then the lines highlight the directions of movement within the coordinate space of the figure. So if you imagine that you're like a fish swimming in a river whose currents are plotted by the stream plot, then if you end up on one of these lines, the current kind of takes you along the path indicated by that line. Okay. So we're, just to mark the time, we're at the official end of our class. So I'm going to keep going, but you know, I recognize not everyone can stay on. So, okay. Oh, sorry, Amelia, did you have a question?
I was just to say thank you. I do have to run, but thank you, and I'll see you on Wednesday.
Okay, take care. Okay, so the next set of figures I'll run through show you, they combine some elements of the plots that displayed the raw data and some elements of the plots that displayed summaries. So these sorts of plots are becoming increasingly popular in the scientific community. because they're often seen as like more honest and open than showing only a summary. And then in practice, combination plots can often be useful, in that they're more open and honest, but they can sometimes look visually cluttered, and that can muddle your ability to effectively communicate. So they tend to be most effective when you have like just a few things to plot or compare. Violin plots are similar to bar plots, but they can show the full density plot for each condition or group. And then in addition, for this example, the individual data points are shown using black dots. So we can see both the individual data points and also how they're distributed all in the same plot, which is kind of neat. Swarm plots also show individual data points with each dot, but then the swarm patterns are displayed in a way that indicates how the underlying distributions look. So if you have like multiple observations at the same position, the dots for those observations start to spread out from the middle. So if you imagine like dividing each color here into rows along the y-axis, then the wider the dots are spread out within each row, the more observations had that value. Boxin plots are also sometimes called letter value plots. The idea is kind of like violin plots or swarm plots, but each box within a given group represents some range of standard deviations from the mean, and then the tops and bottoms of the boxes indicate the range of values within each group, and then the wider the boxes are, the more data points were observed in that range of values. Box and whiskers plots are the older version of Boxin plots. They show the median, upper and lower quartile, and then the maximum and minimum and outliers, which are shown here as diamonds. In box plots, outliers are defined as any data point that falls more than 1.5 times the interquartile range above or below the lower or upper quartiles. And the same is true of Boxin plots. Okay. A joint plot shows both the scatter plot of the data and also a histogram or density plot within each dimension. So in this, and then in this example, there's also a regression line added, and that illustrates the relation between the x and y variables. Another type of joint plot is kind of like the 2D histogram example we saw earlier. But in this style of plot, each range of x and y values is contained within a hexagon, and then a grid of hexagon tiles, hexagons tile the area of the xy plane shown in the figure. So the colors of each hexagon tell you how many data points had values within that range of x and y values. And then the histograms on the top and the right show the data within each dimension, or show how the data within each dimension are distributed. So we get like both how the two dimensions are related and also how they're distributed on their own. Pair grids are used to illustrate how each pair of dimensions in the data set are related. So in this example, the data set has 4 dimensions. So the plot has 4 rows and 4 columns. So the subplots along the diagonal show the histogram for each dimension. So how the values in that dimension are distributed. And then for each off diagonal row and column, you get a scatter plot of how those 2 dimensions are related. So like the first row and second column shows a scatter plot of the first dimension plotted against the second dimension. And then these can get pretty crazy. So when we have multiple groups or conditions with the same dimensions, then we can create pair grids for each group and then show them all in the same figure. So you read this just like a pair grid, but now the colors reflect different groupings within the same data set that we're now able to compare. Rain cloud plots are a relatively new type of figure. They kind of combine violin plots and box and whisker plots and also scatter plots all into the same thing. So you get to see the raw data, a statistical summary through the box plot, and then the full distribution all in one plot. And then in this example, we're seeing color denotes different groups within the data set, and so we can easily compare them. Okay. Next, so all of these are kind of shown in Cartesian space, but that's not the only way to show data. So next, I'll run through a few examples of polar plots, and these are used to plot circular data like angles or other periodic measurements. The most common type of polar plot is the polar area chart, which is kind of like the circular version of a histogram. The values are indicated by the angles of each wedge, and then the amount that each wedge sticks out indicates how many data points had that range of values. And then in this example, oh, okay, take care. In this example, the wedges are stacked, and that shows how each of the three groups contributes to the total. Pie charts are kind of like the black sheep of the data visualization world, but they can sometimes be useful. And the area devoted to each color reflects what proportion of the data are in that color's condition. A target plot is similar to a pie chart, but now the areas are indicated by overlapping circles instead of non-overlapping wedges. And then these plots are also in somewhat bad standing in the data visualization world. So in general, pie charts and target plots are frowned upon because people tend to be bad at judging areas of circles or parts of circles, so they can be, confusing or misleading. But they are an option. Okay. Clustering plots are designed to show groupings in the data. So for example, between observations that have similar values or labels. So I'll show you a couple examples of how these groupings can be illustrated. Probably the most commonly used clustering plot is called a dendrogram. So at the right are individual data points, and then the lines in the dendrogram group data points that are similar. And then as you move up the tree from the right to the left, the lines start to group similar subtrees. And then here, they're also using color to convey additional information or groupings. So in this example, the colors denote the continents where the cities on the right are located. So there's some kind of spatial grouping here. A cluster map is like a heat map that displays the raw data values. Each row of the heat map here is a different observation in the data set, and then the colors indicate the 4 values that make up each observation. And then the dendrogram on the top shows how the dimensions are grouped. So like it shows across observations which dimensions values tend to go together. And then the dendrogram on the left indicates which observations go together. So it shows like which observations had similar sets of values across those 4 dimensions. So taken together, the cluster map is kind of like a joint dendrogram plot that shows 2 types of groupings simultaneously. That can sometimes be useful. When you have measurements changing over time, the most common way to illustrate those changes is called a line plot. The x-axis here indicates time, and then the y-axis indicates the measurement values. And then in this example, we can see how 4 trends compare to each other by showing each trend in a different color and line style. A similar looking plot is called a ribbon plot. the difference from a line plot is that if there's some variability or uncertainty in the measurements, you can indicate that by showing like thicker or thinner ribbons around that time point. So for example, you might want to show the average change in people's height over some time period. And then you could use a ribbon plot to show both those average trends and also the variability in your population. If you want to illustrate something like a social network where people can be friends or communicate with each other, then network plots can highlight connections between entities or data points. The simplest type of network plot is an undirected graph. So each data point, which can be something like a person, is shown as a dot. And then the dot positions and colors might reflect their values or like how the data points are clustered or grouped. And then the lines connecting the dots show which data points are connected. Undirected graphs like this can reveal things like community structure within a larger network. And then in network speak, individual data points or network elements are called nodes. And then the connections between the nodes are called edges. A directed graph is similar to an undirected graph, but in a directed graph, the connections are directional. So for example, in a conversation, person A could be talking to person B, but we might want to distinguish that from when person B talks to person A. And then the connection directions are indicated by arrows on each line. Circos plots or chord diagrams are a relatively new type of network plot that's becoming increasingly popular. The network's nodes here are arranged around the circumference of the circle, and then the ribbons connecting the entries show the edges. And then sometimes the ribbon thicknesses show connection strengths or the numbers of connections between different groups. A circular tree diagram is useful for visualizing networks that are organized as trees. Each dot is a network node, and then each line shows an edge. So for example, like in a phylogenetic tree, the most distant common ancestor would go in the middle, and then as you move from the center to the edge, you can see how different species like branched off from their ancestors. And then like the most recent species would be arranged around the circumference of the circle. Just like colors can carry meaning in a scatter plot, the nodes in a network plot can also be colored to indicate some important property that you might want to highlight. And the edges of a network can also be colored to convey meaning. In an ego graph, the node of a particular node of special relevance or importance is shown at the center, and then its connections radiate outwards. So it's like you kind of pick up the network by one node and then let all the other stuff dangle down. Another widely used type of plot shows information projected onto the surface of the Earth. And this is mainly used to show location data. So the Earth is roughly spherical. And so when you project the surface of the Earth onto a 2D figure, it necessarily gets distorted. But then different map projections make different decisions about what spatial information to preserve or distort when the surface gets flattened onto the 2D plane. And then most, it's worth kind of recognizing or knowing most kind of packages or tools for making geospatial plots support several map projection options. You've probably seen this type of map before, called a choropleth map. You divide up some part of the surface of Earth into parcels, and then you set each parcel's color to show how some value changes across different locations. So these maps are used a lot to show like voting patterns or to highlight patterns that are expected to vary by location. A bubble map is kind of like a geospatial scatter plot. each observation is tied to a specific geographic location, and then it's projected onto the map. And then the sizes and colors of the markers can also carry information. And then geographical line plots are like the analog of a time series line plot, but they display spatial information instead of temporal information. So they are often used to show things like flight patterns or other movement patterns. Okay, and then color can also be used to convey additional information. Animated plots are often really visually compelling. They let us focus in on a subset of the total data set at one particular moment, and then they leverage our ability to synthesize information over time to communicate the full pattern. So just about any sort of plot can be turned into an animation, just like you can change the colors or sizes of different visual elements. In an animated figure, the individual frames of the animation are set up to distinguish some feature of the data. Uber has put out some really amazing visualization tools and data sets. And one example is in this animation that shows commutes from different locations in New York City. This is a famous animation that highlights how GDP and life expectancy are related. Each dot here is a country, and then you can see how both GDP and life expectancy tend to increase over time as the animation progresses. But you can also see when countries fail to carry that trend, when they seem to kind of visually drop out of the larger cloud. This animation is one of my lab's more popular visualizations. It shows people's decoded thoughts as they're listening to a story. So each line is a different person. And then as the lines move through this space, it shows how people's thoughts change at different points in the story. Sorry, Nathan. Yes.
On that last one is, so like where, like, does the space like matter? Like, and like, is that like symbolizing like a certain part of the story? Or
So,
like, or
yeah.
like how do you know like what, like if it's more towards the left, like does that symbolize something?
Yeah, so the axes of this space are relate to the conceptual meanings of the thoughts people are having. So there's a model that goes into this to like define the space and to project people's brain patterns onto that space. But the way to think about it is that points that are closer in geometric space in this figure reflect thoughts that are similar in meaning. And then points that are far apart reflect more conceptually different thoughts. So you can kind of see like each color here is a person. And so like, you know, when people are moving around together, it means they're kind of thinking similar things over time.
That's pretty cool.
Thank you. Okay, so in addition to standard sorts of plots like the ones I've gone over so far, there are some really classic plots that have had a huge impact on data visualization that it's worth knowing about. One of the most well-known data visualizations is the periodic table. So you are likely familiar with it. But the periodic table arranges chemical elements by their atomic number and electron configuration and recurring chemical properties. And visualizing atoms in this way has transformed the study of chemistry. Charles Minard was a civil engineer who lived in the 1700s and 1800s, and he invented the concept of flow maps. And his most famous figure shows Napoleon's major losses during his, 1812 Russian campaign. So the tan line shows the path into Russia, and then the black line shows the path back to France. And then the line's coordinates show geographic locations, and the thicknesses show how many troops are at that location at that moment in time, where the time points are labeled along each path. And then the bottom panel also shows temperature expressed in degrees below zero at different time points. So altogether, the figure succinctly represents 6 data types in 2 dimensions. You've got number of troops, distance, temperature, latitude and longitude, direction of travel, and time. So this is often held up as an ideal data graphic because of how succinctly and intuitively a large, really huge amount of information is presented. 538 is a data science and statistics blog that's best known for its simulations used to predict election outcomes. And this is one of their graphics used to illustrate potential outcomes of the 2020 election. And the winding snake depiction here does a really nice job of indicating the predicted electoral vote breakdowns by state. Okay, so last I wanted to just end with a few tips and tricks. So there are some common principles that underlie the most effective data visualizations. So one principle that I linked to in module 2 was articulated by Edward Tufte, who's a famous data visualization guru. And the idea is to maximize what Tufte calls the data to ink ratio, which you can think of as like the amount of information that each spot of ink conveys. So according to Tufte, maximizing the data to ink ratio will lead you to produce figures that are more intuitive because they force you to remove any extraneous detail that's not specifically conveying information. And that principle also extends to things that aren't necessarily ink per se. So for example, you should minimize the use of unnecessary variations in color and size and shape, et cetera, that aren't directly improving the figure's ability to convey information. So whether or not you follow Tufte's principle, the most important thing is to do whatever you can to make your figures intuitive and readable by your audience. Another consideration is how you use color. So you can use color to intentionally highlight important data points or patterns, or to illustrate connections across figures. And then when you use multiple figures or panels within a figure, it's also useful to consider how much visual weight each element takes up, or like how much each figure or part of each figure draws your attention. You want people's attention to be drawn to the most important parts of your visualizations. And then finally, none of the figure styles or principles that I've mentioned today are hard and fast rules. So use the ideas that I've mentioned to help guide your design process, but you can break any rule if it allows you to communicate more effectively. Okay, thank you for bearing with me. Sorry for going over. That's all I have today. So remember to take a look at assignment 2 and come to class on Wednesday with some ideas for that assignment so that we can workshop then. Sorry, did you have a question?
I had a quick question. Yeah.
Yeah.
So are we expected to be able to produce those types of visualizations?
Not yet. We'll learn how to do that. But yeah, you don't have to yet. So for assignment 2, you'd just be sketching out a drawing of a figure. It doesn't have to be accurate.
Okay. So I've had an idea for my thing for the second assignment, and I was thinking, do I make fake data? Do I try to make it on Excel? So it's just a sketch.
Yeah, you certainly can make it in Excel, but you don't have to. Yeah, we'll cover how to actually do this stuff. It's really just to get you thinking about, okay, if I could visualize this data set, how would I? And since you may not actually have the tools yet to analyze your data set, you can just make up the whole thing. So make up what your results might look like given what your data set is, and it can be a fake data set, so it doesn't actually have to exist.
Okay. Thank you.
Sure.
Thank you.
All right. Oh yeah, did you have a question?
Oh no, I was gonna say I'm probably gonna head out, but thanks.
Yeah.
Thanks
Okay.
for going over all this.
Okay. All right. See you on Wednesday. Take care.
Bye.
Bye.
Bye.